All right. So you've been sending us articles about this dark matter,
Yeah.
lots of them. And we're going to do a deep dive and try to figure this out.
Cool.
Basically, like over a quarter of the universe is made of this stuff,
Right.
but it's invisible.
Yeah.
You can't see it.
It's wild.
It's crazy. And there are these two kind of like contenders for explaining what it is,
Uh-huh.
WIMPs and Axions.
Yeah, two of the leading candidates.
So where do we even begin with this?
Well, I think we got to start with WIMPs, right? They were
Alright.
like the front runner for a long time.
Okay.
They're these hypothetical particles, right?
Okay.
And the idea is that they interact through this thing called the weak nuclear force.
Okay, so what's so weak about this force?
Yeah, so like it's weak compared to something like the electromagnetic force,
Got it.
which is what governs light and electricity and all that stuff.
Okay, so how did WIMPs become such a promising candidate?
So there's this thing called the WIMP miracle, which basically the math worked out perfectly.
Oh, wow.
Scientists calculated like if WIMPs existed and if they were created in the early universe, right,
Mm-hmm.
they would be like the exact right amount
Well,
to make up the dark matter that we see today.
it's like the universe was telling us.
It seemed too perfect.
Wow. So what happened?
Well, they built this giant particle accelerator.
Oh, yeah, the Large Hadron Collider.
The LHC, yeah, the biggest one ever.
So easy expensive.
Oh, for sure. And they were supposed to find WIMPs there,
Uh-huh.
but no matter how hard they looked, they couldn't find them.
Nothing.
Nothing.
Oh, wow. So what did that mean for, the whole field of dark matter research?
Well, it was a pretty big setback for the WIMP idea.
Yeah, I bet.
Like, it forced scientists to kind of go back to the drawing board,
Yeah.
and that's where Axions come in.
Okay, so these Axions, they're kind of like the underdog, right?
Yeah, totally.
So what are they and how are they different from WIMPs?
So Axions, they were actually proposed back in the 70s.
Oh, way back.
Yeah, to solve a totally different problem. It's called the strong CP problem.
Strong CP problem.
Yeah, it's kind of a mouthful.
Yeah.
But basically, it's a problem with the strong force.
Okay, and remind me, the strong force is...
That's the force that holds, like, the nucleus of an atom together.
Right, right.
So there's this weird thing, like, the equations predict this asymmetry
Yeah.
that we just don't see in the real world.
So, like, the mass doesn't add up.
Exactly.
All
And Axions, they're kind of like the missing piece of that puzzle.
Okay,
But, initially, people didn't really take them seriously.
why not?
Well, because they seem to interact really weakly with matter.
Right, right. So how did they go from being dismissed to being, like, a leading candidate for dark matter?
So this modified version came along called invisible axions.
Invisible Axions.
Yeah. And it turned out that these invisible axions, they could actually be dark matter.
Okay, so they're invisible. They solve this strong CP problem.
Right.
But how do we even find something that doesn't interact with anything?
Yeah, that's the tricky part. Detecting them is super hard.
Yeah.
Like the current methods, they use these really powerful magnets
Uh-huh.
to try and get the axions to convert into photons,
Which are?
particles of light.
Okay. So we're basically trying to make dark matter visible.
Kind of, yeah. It's like trying to hear a whisper in the middle of a hurricane.
Wow. Have we heard anything yet?
There have been some hints,
Oh.
but nothing like definite.
Okay.
One of the really exciting areas of research right now is looking for axions around pulsars.
Pulsars.
Yeah, these are like rapidly spinning neutron stars
Right.
with like crazy strong magnetic fields.
It's like giant cosmic magnets.
Exactly. And the idea is if axions exist
Yeah.
and they interact with these magnetic fields, they might produce radio signal.
That we could detect.
Yeah.
So it's kind of like using these pulsars as amplifier
Yeah.
to make the axion signal louder. Wow, that's amazing. Now, one thing I was thinking about as I was reading all this
Yeah.
is this idea of like fine-tuning.
Yeah.
Like some scientists think that maybe axions are too good to be true.
Yeah, that's a valid point.
So what's that all about?
So to make the axion models work, right?
Yeah.
Like to fit our observations of dark matter,
Yeah.
you have to adjust certain parameters very precisely.
Okay.
And, that makes some people uncomfortable because it feels a little bit like we're like forcing the theory to work.
Right, right. So it's not as like elegant as it could be.
Exactly.
So while axions are definitely like a leading candidate, it's not a done deal.
Not at all.
There are still some like big questions.
Absolutely. But that's how science works, right?
Yeah.
It's a process.
Yeah, it's all about testing and refining.
Exactly. And even though there are these open questions, axions are still a really compelling candidate.
Yeah.
I mean, we just haven't found anything better yet.
So like what's the main takeaway for our listener here?
I think, the whole story of WIMPs and axions, it's a really good example of how science works.
Uh-huh.
We have this, like, favorite theory, right? WIMPs.
Yeah.
And it was tested really rigorously.
At the LHC.
And then when the evidence didn't support it, scientists were willing to, like, shift gears.
To adapt.
Yeah.
And that's like a good thing.
That's how we learn and grow.
And ultimately, like whether we find out that dark matter is made of axions or something else entirely,
Right.
That journey, that process of discovery is
Mhm.
what's really exciting.
Totally.
So if we do find dark matter, whatever it is, what will that tell us about the universe and our place in it?
Yeah,
That's something to think about.
for sure.